We have some popular equations in fluid mechanics. The first and the most popular one is called continuity equation. Continuity equation is actually based on the concept of the conservation of mass. It means that, for example, if we are not like the no water loss, and if we have no leakage within the system or additional flow coming to the pipe, the mass and the quantity of the water entering the pipe, for example, this section at point A, must equal the amount of the flow existing the pipe here, for example, at point 2. So with this kind of relationship, we can easily write Q1, or the flow rate at point 1, or the flow discharge at point 1 is equal to flow discharge at point 2, assuming that we don't have any water loss in between and there is no the additional water comes in between these 2 points. So if we can just write that the flow discharge is written like this, Q1 and the Q2. And Q1 can be written as multiplications of the cross-sectional area, A1, times the velocity, V, at point 1, A1, V1. And at point 2, the flow discharge can be written as A2 times V2. So that's like the discharge, a new term that we're just going to learn here. So in this case, we have like the flow discharge at point 1 is equal to the flow discharge at point 2. And discharge is the amount of the volume of the water that can pass over the time. And the unit of the discharge is the volume over the time, which is equal to the cross-sectional area times the velocity at any point. And if you have a pipe, a single pipe is split into 2 separate pipes, for example, or it could be like the more than like the 2 pipes split into like the multiple pipes, we can write based on the continuous equation, we can write, for example, Q1, or the original or the initial pipe flow discharge of the initial pipe is equal to the sum of the discharges for each pipe. For example, if it's split into 2 pipes, Q1 is equal to Q2 plus Q3. That is the continuity and the continuity equation. Let's go with the one simple example. We have, assuming that we have the pipe that with a diameter of the 0.2 meters, increase gradually to 0.3 meters from section 1 to section 2. And if the pipe carries discharge of the 0.08 cubic meters per second of water, the question here, what are the velocities at the 2 cross sections? Okay, so first of all, for point 1, we have the diameter and we have the velocity and we have the flow discharge. By using the equation of the flow discharge, we can easily calculate the velocity at point 1. And if you have the velocity at point 1 and the diameter or cross-sectional area at point 1, as we have the cross-sectional area at point 2, we can easily calculate the velocity at point 2 based on this equation. Okay, Q1 is equal to Q2, or A1 V1 is equal to A2 V2. So we're just going to write here, very simple. Q1 is equal to A1 V1. So A1, so cross-sectional area, is the cross-sectional area of the diameter. Diameter is given to us 0.2 meters or 20 centimeters. So we know the formula for cross-sectional area is pi diameter squared, or 0.2 squared, over 4, which is equal to 0.0314 square meters. Okay, and for cross-sectional area 2 as well, we can have the diameter. We can easily write pi 0.3 squared over 4, which is equal to 0.0707 square meter. So if you have A1 and A2, simply we can just put in the flow discharge for the first one, for the first cross-section, 0.08 is equal to, as a Q, is equal to A1 cross-sectional area is like a 0.0314 V1, okay? And by solving this equation, V1 is equal to 2.548 meters per second. We can either use the equations that A1 V1 is equal to A2 V2, or because we have the Q, we can directly use the Q for the second equation. Q is equal to A2 V2. We can substitute Q in here on the left-hand side, and the right-hand side A2 can be replaced from here, substitute from this part, 0.0707 V2, and the V2 is equal to 1.132 meters per second. Let's go and look at another example. Another example is talking about the water flows through a branching pipeline as shown in this figure. We have like a one pipe is split into two pipes. If the diameter D2 is 250 millimeters, okay, and velocity at pipe 2 is given 1.77 meters per second, and velocity at point 3 is also given. That's it. So velocity at point 3 is 1.43 meters per second. So the question here is to calculate the D3, the diameter point at pipe 3, which is required for if the Q3 is equal to 2Q2. So the Q3 is twice the Q2. Okay, that's like the relationship. And for section B, what is the total discharge at section A? So by using this assumption, Q3 is equal to Q2, we need to just replace or substitute the equation for the flow discharge, which is the VA. If you replace the VA, we have V3, we have V2, and we have for a cross-sectional area, we have the D2 for the A2 we can calculate, and the only thing is remaining is the D3. So we can just look at this one as well. So, and also for the total discharge is the sum of the total discharge of the Q2 and Q3, if you have like that one together. So let's see how we can calculate this one. Okay, so we have the equation Q3 is equal to 2Q2. We can simplify. Q3 is A3 V3 is equal to 2A2 V2. And then A3 is like a pi D3 squared over 4 times the velocity, which is for V3 is like a 1.43, is equal to 2 times pi 0.25 squared over 4 and times velocity, which is like 1.77 meters per second. In this case, D3 can be calculated 0.393 meters by solving these equations. Very simple. For section B, we need to calculate the Q2 and Q3. For Q2 can be calculated here, pi 0.25 squared over 4 times V2. V2 is given here, 1.77. And the Q2 is equal to 0.07887 cubic meters per second. Q3 is twice Q2, so 2 times 0.087 is equal to 0.174 cubic meters per second. And the sum of the Q3 and Q2 will give us the Q1, which is equal to 0.261 cubic meters per second. So that is the example for the second example of the continuity equation.